Okay, welcome back, everybody. So, we ended the previous lecture in the following place. We're considering wave equation. We have now replaced our constant with kind of the, original quantity showing up in the derivation of the wave equation. So this t in rho, so t over rho here is playing the role of our c squared. So a couple of assumptions. So we assumed that our solution was C2. We assumed that the data given were smooth with compact support here. Now what that meant, as I said, is that they vanish off a compact set. So there exists some big R off of which these are zero. And so the only non-zero portions of these can be fit in some compact set minus R to R, right? So they look something like this or this, but not something like that. Okay. So if the initial data has compact support, then by D'Alembert's formula, since we know exactly the form that U takes in terms of phi and C, this solution also vanishes off compact sets. So the solution also has compact support if the initial data do. And I defined two quantities. One, the kinetic energy related to this solution, and the potential energy related to this solution. So, um, what what is where did these come from? So one, you might be okay with the form that this takes, because if you remember, kinetic energy is 1/2 mass times velocity squared. So this is 1/2. This is now a mass density function. Right, so this is rho is mass density, and u sub t is velocity, so this is velocity squared here. So you might be okay with this expression being kinetic energy. See that potential energy is, it's okay if it's this expression. It might, you might be able to convince yourself that it's reasonable to expect potential energy to be proportional to this tension, right? The other thing is, you might ask yourself, like, what is the relationship between this potential energy and, say, like this quantity? Well, maybe rather than thinking about this quantity itself, you might think of, like, the absolute value of this slope here, right? So you might expect the potential energy to increase with this, right? So if this is the slope, then the higher the slope, or the more extreme the slope, right, the greater the restoring force that's trying to return the string to its equilibrium position. So that, expecting the potential energy to increase with the size of this seems reasonable. Okay, so rather than deal with, of course, absolute values are terrible. The way we deal with them whenever we can is, instead of dealing with them, of course, wherever this is large, well, this quantity is going to be large. So these are my kinetic and potential energy here, and the reason for defining these, right, is I was interested in investigating the conservation of total energy. Total energy is the sum of these two things, and so total energy is E of t, which is defined to be the sum of the kinetic energy plus potential energy. Okay, writing these together, so there they are on the screen again. I'm going to write these together as, so this is how the total energy is defined. These two things written together, this is 1/2 times the integral from minus infinity to infinity. The kinetic energy term is like rho u sub t squared plus t u sub x squared dx. Okay, there's my total energy. Okay. Now, what I want to do is first, I wish to see how my kinetic energy changes over time. Okay. Well, if I want to know how this changes over time, of course, the quantity that I want to compute is its derivative with respect to time. So what is the derivative with respect to time of the kinetic energy? So this is ddt of what? Of 1/2 times the integral from minus infinity to infinity of rho u sub t squared dx. Okay. Now, why am I able, for instance, to do anything with this quantity, right? The idea here is that I want to be able to pass this integral under the integral sign. Here, I don't have to worry about making too hard of an argument. We're going to see a little bit later when we prove Duhamel's principle today how we have some theorems. They're listed in the appendix of the textbook, so I will show those on screen later for if you want to justify differentiation underneath an integral sign in kind of this fashion. So if we want to address that, like when exactly are we allowed to move a derivative under an integral sign, there are theorems, like I said, in the appendix for that. Here it's actually a little bit easier because everything involved here has compact support. Right, so everything involved, so these are smooth, U has compact support, and so what am I able to do here? So I can actually move this under the integral sign, no problem, so that when I do this, I get 1/2 as the integral from minus infinity to infinity of the derivative with respect to t of rho u sub t squared, right, dx. That's what I get. Okay. All right. So rho doesn't depend on t, so that's totally unaffected here. What do I get with it? So I have the derivative with respect to t of u sub t squared. So chain rule tells me this is, I can go ahead and move rho out. So this is 1/2 rho times the integral from minus infinity to infinity of 2 u sub t times the derivative of u sub t with respect to t. So this is u sub tt dx. 2 cancels the 1/2 here, and so what I'm left with is rho times the integral from minus infinity to infinity of u sub t times u sub tt dx. So that's what I have, right? Okay. Now, there's something a little different here. So, of course, you notice this u sub tt term. The u in question is not just some random u. It satisfies the wave equation, right? Let's multiply both sides by rho. And what this tells me is that rho times u sub tt is equal to t times u sub xx. Right? And so rho u sub tt is equal to t u sub xx. So in my expression here, rho times u sub tt, that's t u sub xx. And so actually I can rewrite this as t times the integral from minus infinity to infinity of u sub t times u sub xx dx. Okay. Well, now what? Now comes something that is extremely important for, this is a trick that can be done for a variety of different PDEs, usually, very closely related PDEs, but um, this type of method that we're doing here, I'll kind of reflect on it after we're done, after it has done what we wanted it to. But the next thing we do, and this is very important, okay, we can integrate by parts to shift derivatives as we like in order to manipulate these expressions for our gain, we'll say. Okay, so this approach can be repeated for a variety of problems, and it's very powerful. In fact, what's nice about this as well is that it can be done for higher space dimensions too. It's just that the integration by parts then takes the form of Gauss-Green identity, Stokes theorem, divergence theorem, that type of stuff, right? The higher dimensional analogs of integration by parts. So that's what's happening here. Okay, so now we want to shift derivatives. One of these x derivatives, we want to shift it over to this u sub t here. And so how do we do this? Doing integration by parts here, I'll put that at the top. i.e., this implies that our derivative of kinetic energy, which we said is t times the integral from minus infinity to infinity of u sub t, u sub xx dx. Let's think about like basic integration by parts, how this works. So what's going to happen here, this is going to be, so I need a u and a dv, right? I'm going to have my u be this thing because I want the derivative to happen on this term. And my dv is going to be this u sub xx dx because that's the thing I want to get rid of a derivative on. I'm going to be integrating it. And so my first thing, I have this, of course, multiplying everything. So this is like t times u v. So if this is, maybe I'll use pen. If this is my dv, right, and this is my u, then the expression, of course, I get is like tuv minus, right, what I should get is tuv minus t times the integral from minus infinity to infinity of v du. And of course, since this is a definite integral, this is the expression that I should get. So let me actually write out what that is here. So this is t. I've said that u is this u sub t here, so this is t u sub t. If dv is u sub xx dx, then v is u sub x, and that is evaluated from minus infinity to infinity, minus t times the integral from minus infinity to infinity of v, which is again u sub x, du. So this is u sub tx, right? So this is like u sub tx, u sub x dx. So I've moved one of these x derivatives over on to u sub t. And so this is what I get. Okay, now here's a very, very important step here, right? Terms like this, when I do this process, right? Terms like this, I do not want sticking around. I want those to disappear. So I have to ask myself, is there a reason why I can justify this term being 0? Well, yes, of course, right? It's that my data is compactly supported, right? My data is compactly supported, so these quantities here are compactly supported, right? We can dismiss those boundary terms because for any fixed t, both of these will have compact support. Okay, and so this is 0. That's very important. Okay. And so what I get is that this is equal to minus t times the integral from minus infinity to infinity of u sub t x u sub x dx. Okay. Oh, but wait. This thing we have put in a very specific form. Right? We've put in this, like you might say, what was our purpose of doing this? Because we were able to see ahead, and we were able to see, wait, what is this really? This is really the same thing as minus t times the integral from minus infinity to infinity of what? This is really, this expression is the derivative with respect to t of 1/2 u sub x squared dx. Do we believe this? Let's check. The derivative with respect to t of 1/2 u sub x squared is going to be 1/2 times 2 times u sub x times u sub xt, because I'm taking the t derivative now, right? So just by chain rule, this would become u sub x times u sub xt or tx. There we go. That's exactly it. So it's this thing. Moving this out, this is the derivative. Or maybe I can move the minus sign out too. This is minus the derivative with respect to t of t times the integral from minus infinity to infinity of u sub x squared dx. But what is that? Oh, sorry. This is t over 2 here. Now we're happy. So what is this expression? That's my potential energy. So this is the potential energy, T, which means that I've shown that this is minus the derivative with respect to T of the potential energy at T. So that is what the derivative of the kinetic energy is. So what I've shown is that the derivative of the kinetic energy with respect to T plus the derivative of the potential energy with respect to T is equal to 0. But wait, the energy, the total energy, was defined to be kinetic plus potential. And so really, since I showed that the sum of the derivatives of those things is equal to 0, and of course the derivative is a linear thing, then what I have really shown here is that the derivative of the total energy with respect to t is 0. But if the derivative of the total energy is 0, this means the total energy is constant. Which is another way of saying the total energy is conserved. Now, you might say, wait, why is this so important if basically, you know, we did all this computation just to show that the energy is conserved, right? Once we do that, isn't that it, right? Once we've once we've shown it, once we've shown conservation of total energy, well, we can't re-show it, right? So what is the good of such a method? Um, in terms of reusability. So here is why this is important. So this sort of thing, defining this energy quantity as we've done here for our problem, our IVP, and then computing derivatives of it to make some claims about the behavior of solution or properties of the IVP itself. This is called the energy method. Okay, so this is called the energy method. Okay, and why is this important? Maybe this is like a double star fact. We can use this to show that the associated IVP our favorite wave equation. So here, again, this is an infinite string, and our initial displacement is phi, and our initial velocity is c. Okay. We can use this to show that the associated IVP has a unique smooth solution. How? Okay, so the first thing is to suppose, right, here's our proof. Suppose that u sub 1 and u sub 2 both solve, we'll say asterisk here, right? And when I say asterisk, of course, I'm not talking about just the PDE, I mean all of these, right? The initial conditions as well. So suppose that u sub 1 and u sub 2 both solve asterisk. Okay, define u to be u sub 1 minus u sub 2, say. Then u would solve what IVP? U sub 1 minus u sub 2. So we know that this still solves the wave equation. This is because the wave equation is linear, and this is my principle of superposition, right? So my principle of superposition tells me I have a linear equation. Any linear combination of solutions is going to be a solution. So this is going to solve the IVP, which I'll denote as smiley face. Okay, so it solves the IVP smiley face, which has PDE, still wave equation. I'm not going to write the domains here. But now, what are my initial conditions? Since both u sub 1 and u sub 2 solve asterisk, so both of them have initial conditions phi and c respectively, then their difference is going to have 0 initial conditions, right? So this is going to have initial displacement 0 and initial velocity 0. Okay. The question, what we want to show, that the solution to smiley face must be identically equal to 0, i.e. u is identically equal to 0, i.e. since u is u1 minus u2, this shows that u1 and u2 are identically equal to each other. Think about what we did. We started out supposing we had two distinct solutions to this, and we have arrived at, oh, actually those two distinct solutions, they have to be the same. Right, so any two solutions to this IVP they have to actually be the exact same solution. So solution's unique, so I'm done here. So then what I want to show is that the solution to this must be identically equal to 0. Okay. Well, here's the question, right? What is this? Right, if I go to the energy, so now we already know that this computation here, right, note this energy method we did not refer to the only reference that was made to my initial data was to guarantee compact support so that the computation worked out. But other than that, right, the only thing I needed was that everything here solved the wave equation, right? And so I had already shown that my total energy is constant, right? So I've already shown that the derivative of the energy is 0, so it's constant. So we already know that dE dt, right, t is 0. But note that E of 0 is also equal to 0. Well, what is E of 0? So E of 0 is going to be this energy quantity with, I've suppressed notation here, of course, to make this not a total nightmare, right, to write out repeatedly. Here I'm going to have the initial data at C. Here I'm going to have a derivative of phi here when I plug in the initial condition. If I plug in 0 here, though, let's go back to my smiley face. For this IVP, I can carry out the exact same computation on the energy, except I have initial conditions 0. Thus, when I plug in 0 for my T here in the energy expression, I get 0. So I have an energy that is 0 at 0, but this computation of its derivative tells me that it's constant. Thus, this means that the energy, again, we're doing the energy for this IVP, right? That's the whole idea. So for this one, the energy is identically 0 for all t. It's always 0. But what does it mean if this expression is always 0? Notice how this is. 1/2 mass density here, t here, but the expressions u sub t, u sub x, these are both squared. What does it mean if this is always identically 0, right? So if this is just always 0, identically 0 in the sense that for all t, this quantity is always 0. What does that mean? It means that u sub t and u sub x are not just 0 at t equals 0, but they are also identically 0. So E sub t being identically 0, recall, right, this is, maybe I should just write it on the same page. This is saying that 1/2 times the integral from minus infinity to infinity of rho u sub t squared plus t u sub x squared dx. If this is identically 0, right, this implies that u sub t and u sub x are identically 0. Not just at t equals 0. But if that's the true, or if that's the case, then our solution, u of xt, must be constant for all x and t. But we know that initially it's 0. So u of xt must be identically equal to 0. But that's exactly what we wanted to show. That shows that u sub 1 has to identically be equal to u sub 2. And thus we have shown that our IVP has a unique solution. So we have shown uniqueness. The IVP in question, of course, is this one. Okay. So it may seem that, I have spent kind of a lot of time here on this energy computation, but the reason for that is that this method of using the energy to show uniqueness is something that can be done for other problems. This can be repeated, and where you do some energy computation which involves differentiating under some integral signs, integrating by parts, using the PDE itself to manipulate these expressions to get this derivative as 0, or in other cases to get that, say, like the derivative of the energy is always negative, so it's always decreasing. Things like this. These sorts of computations, called the energy method, can say a lot about the PDE in question, and they can be applied to more than just the wave equation. So this is the key. So this is definitely worth it to have a look at. Okay. So previously I had talked about the wave equation really modeling like transfer of energy along string. Right? I believe that's how I had worded it. So what is it that's actually going on here? So one thing to note is, going back to this, while the total energy is conserved and is constant, it's not true for the kinetic and potential energy. Okay, the kinetic and potential energy are going to vary at different times t, but it's the total energy that remains constant. And so when we're thinking about wave propagation here, modeled by wave equation, what is it that's going on here? What is it that's transported along the string? Really, it is basically a transfer of kinetic to potential that is happening, and back again, right? Transfer of kinetic energy to potential energy and vice versa. Transported along the, so this is transported along string. This is what it is that's going on. Okay, so when I said that this is like energy being transported, this is what I meant. Okay. So think about this. Think about both of the previous examples we did in the last lecture, the plucked string and the hammer blow. Think about how this relates to those things. Okay. So what if now we look at an inhomogeneous wave equation, right? What does that mean? So if we have all expressions involving derivatives on one side of the equation, right, like we like to do typically, say we have wave equation with initial conditions and it looks like this. So u sub tt minus c squared u sub xx is equal to some function f of xt, and again we have initial displacement and velocity phi and c. Okay. On the same, I'm not going to rewrite all of these. Okay, so these are on the real line. All right. So this is like a modified wave equation. How can I be sure that this is really still modeling kind of similar thing? What is this? What is this thing that's going on? The idea is this is a forcing function or body force or a source term. Okay. Sometimes we'll just call it the right-hand side function. But this is an example of having a source term, or more generally, this is an inhomogeneous example of a wave equation. So the right-hand side, we put everything else involving the derivatives of the wave equation on the left-hand side. Everything on the right, this right-hand side thing doesn't involve, of course, solution u itself. That'd be a different equation. But so this is just a function of x and t here. Okay. So for instance, maybe this body force is gravity, in which case it would just be like a constant here. Maybe it's some other more complicated uh, external force I'm thinking about. Okay, and so it turns out that we have the following theorem. I'm not going to prove this, but it is pretty straightforward. I can extend D'Alembert's formula to inhomogeneous wave equations in the following way. So if u solves, I'm going to call this star, then the actual form of this thing is D'Alembert's formula. If you like, this is like the homogeneous part, right? Thinking back to ODE of, homogeneous plus particular. Plus 1 over 2c times the integral over d of f of, I'm going to use variables y tau here, dy d tau, where d is exactly the domain of dependence. Remember, we drew the domain of dependence previously, this shaded triangle region. So it's the domain of dependence associated to xt, right? So it's this, maybe I'll just draw the picture here, right? If this is xt, the domain of dependence is this shaded region. Here's x in the middle. This is x minus ct and x plus ct. So the domain of dependence is this thing. So this is d. Okay. So what is this relative to what it is that's going on here? Of course, we recognize this is the solution to the associated homogeneous equation where f is 0. That's just D'Alembert's formula. So then what is this extra term we're adding? Like, what is kind of its interpretation here? Well, this is like, what is it that I'm adding to my solution here to make this different? It's that I am integrating this, so I'm computing displacement here. So in order to compute displacement, I do my usual thing from D'Alembert's that we explained what it is that's going on. But then to actually get my like accurate displacement, I need to do this integration, which is like the body force history, right, over the region of space and time that matters, right? The region that I know contributes to displacement value here. So this is like my body force history. Okay. So, note like it's not some kind of integral over like all of this everywhere. It's only an integral over the relevant points, right, in the xt plane. Right, the points that contribute to the value of the displacement at xt. Okay. So that's one nice thing. We can actually prove this with a method that is a much more general approach to inhomogeneous equations like this, period. And this method, you can use the method to tidy up a proof of this and be done with it. I'm not going to do that. I might leave that for, you can check on your own, or I might actually assign it in your next homework, which is coming, by the way. I didn't upload it last night, but I'll upload it today, and it'll be due on Friday, late. But basically, this method that we're going to do applies not just to the wave equation, it also applies to the heat equation, it applies to a bunch of different equations in general. So it merits talking about that method rather than this specific proof. And that method can be adapted to prove this. That method basically proves this outright with a little bit, with a couple more lines, pretty much. And so this method is Duhamel's principle. Duhamel's principle, this is a method for dealing with inhomogeneous linear PDEs. Okay. You can extend this to higher space dimensions quite easily, so it's also good in that way. It can be used not just for the wave equation, it can be used for many, many other linear PDEs. So what this method actually is, there is an exercise in this section that shows you what it is, but what this method actually is your favorite method from ODE, variation of parameters. That's essentially what Duhamel's principle is. Okay. So let's do the setup for Duhamel's principle. I'm going to prove why Duhamel's principle works. This is going to require me to use some facts, a couple facts from the appendix, which I will point out, I will put on screen. One of them is the one I mentioned earlier, which tells you when it is legal to move that derivative under the integration sign and be happy. The other one deals with a type of what's called a Leibniz formula. So let's see, what is Duhamel's principle? So suppose we wish to solve the inhomogeneous IVP star. Let's go back here. What is star? It's this one. Okay, so it's inhomogeneous, so it's the wave equation, but now I have this force term, right? And I have my normal initial displacement velocity. Okay. Well, actually, by superposition, think about why this is. It is sufficient to solve the following. So it is sufficient to solve u sub tt minus c squared u sub xx is equal to f of xt with 0 initial conditions. All right. Again, on the same regions, I'm not going to rewrite them every single time. Okay, but it is helpful here. Okay. So, why is it sufficient to solve this? Because if I had a solution to this, what could I do? I could add it to a solution to this. Do I know how to solve this? Yes, of course, by D'Alembert's formula. All right, this is exactly what it is. The IVP for the wave equation. I exactly know how to solve this. So D'Alembert's formula gives me a solution to this. If I have a solution to this, if I can solve this, then a solution to this generic IVP star, where I have general initial conditions, can be obtained by just adding these two. Right? Since I already know how to solve this, though, I don't need to worry about that. So all I need to do is solve this one, right? So this is a simpler thing. I have 0 initial conditions here. So this is a simpler thing to solve. Okay. And so, now what? The idea, the thing that really defines Duhamel's principle, is add another time variable or parameter s. Okay. And this s is some non-negative thing. Oh, why did I write s there? So it's some non-negative real number. And then for each fixed s, consider an indexed solution. This is indexed by s. So this is by s. And this indexed solution I'll denote as wxt semicolon s to indicate that it is indexed by s to the following IVP. So the IVP in question is w sub tt xt s is equal to c squared w sub xx xt s, so the homogeneous wave equation. And that is solved for x in the reals and for t greater than s and W X S S is 0, and W sub T X S S is F of XS. And that's for X real. Now this is very confusing. What is it that I do here? So what have I done? Instead of solving an inhomogeneous equation like this with 0 initial conditions, I solve a homogeneous equation. So this index, what's the difference between this indexed equation and this IVP? Well, the wave equation portion of it is homogeneous, right? There's no forcing term. And instead, I've incorporated that forcing term here into one of the initial conditions. Okay. Now, Duhamel's principle, the way that this works is that, like, why did you incorporate it here? Why did you incorporate it on this derivative with respect to t instead of the initial displacement? The way that this works is the source function goes in the initial data corresponding to one time derivative less than the total number of time derivatives. So we have 2 total time derivatives in this equation, so it goes here, right, in the one time derivative part of the initial data. That will make sense. What I just said will make sense when we revisit this for the heat equation. So when we do this for the heat equation, we will be able to use Duhamel's principle in the exact same way, and the placement of that source term for the heat equation will match what I just said. Okay, but what is it that you're actually doing here, right? Well, what you're doing basically is you are now solving the homogeneous wave equation with your time starting at t equals s instead of t equals 0. And then the initial conditions, right, are now like initial conditions. They're conditions at t equals s, right? So your initial time is t equals s instead. You're basically replacing the initial time with some time t equals s and solving those for each fixed s. Okay. Now, what does Duhamel's principle actually say? Like, I've given this a name up here, Duhamel's principle. What does Duhamel's principle say about this thing? Okay, so maybe I should, we'll denote this by, asterisk, I guess. That makes sense. So what does Duhamel's principle actually say? The solution to asterisk is given by u of xt. Oh, sorry, not asterisk. I should say the solution. That's confusing. Let's go back here. If I call this, let's call this box. Okay, box plus. Okay. So the solution to box plus, which is this inhomogeneous wave equation with 0 initial conditions, is given by u of xt is the integral from 0 to t of w of xt s ds, where w of xt s is a solution to asterisk. which is this indexed problem. Okay. So it turns out that this formula here actually reduces to our modified D'Alembert's formula for the inhomogeneous equation, this fact here. So this expression, right, can actually be obtained from Duhamel's principle. And there's an exercise in this chapter, I think it's exercise 17, is the one that asks you to show that. So let's prove Duhamel's principle. Okay, so proof of Duhamel's principle. So let's say that I have a U that satisfies this box. So say U satisfies box plus. Okay. Then let's actually no, this is a here. Let's do something a little bit different. Let's do something a little bit different. Rather than going about it this way, let's actually verify first that this formula here for U actually works, actually solves the box plus PDE here. So first, if I'm wanting to check that this actually works here, I want to differentiate this thing, obviously, with respect to t and x twice in order to verify that this works. So let's verify that this is indeed a solution. Okay. So if I'm going to be taking derivatives with respect to x, I need to know how to differentiate under this sign. So what are the rules for differentiating under integral sign? You can find these in the appendix. The first one I'll be using is this is called theorem A10, I believe. Let me bring it a little bit closer and then focus. Here's theorem A10. Tells me if I have a domain in Rn and a continuous function of x and t here, defined for my domain and for t in some interval. Suppose the following. Suppose that those partials indicated there are continuous on that direct product of of domain and the time interval. And there exist integrable functions g and h that dominate the partials and f itself in the way indicated. Then this function defined by here, notice that these integrals are with respect to dx is continuous and differentiable function. And this derivative with respect to t, this is not one of the derivatives being integrated with respect to, can be moved under the integral sign. Okay, most functions we encounter are going to satisfy this. This is just to bookkeep a little bit. Okay, and so I can indeed do the partial derivatives that I want to here. And so what does this lead to? I can take double x partial of u, and what do I get? I get the integral from 0 to t of the double x partial of w x t s ds. Okay. Now define big F of t to be my function u of xt for fixed x. So for some fixed x, define big F of t to be u of xt. And I want to compute big F prime. Right? Well, here, if u is defined in this manner, I'm taking the derivative With respect to this expression, the t here, sorry, I'm taking the derivative with respect to t of this expression. T here shows up in the limit of integration. How do I handle this sort of differentiation? Well, there's what's called Leibniz rule for this. And here's the other. So here's the other expression I need. This is used directly to verify this. So here it is. If you have a big F of t defined in this manner, where little f is smooth function in both the variables, then big F prime is f of tt plus the integral from 0 to t of f sub t ts ds. So this is how differentiation with respect to t of a thing like this works. Okay, so have a look at that. So with those two theorems in hand, I can immediately, let me refocus here. I can immediately say, oh, well, this big F prime, this is really u sub t x xt, which is what? This is the integral from 0 to t of w sub t x t s ds. Using that same property yet again, what is the second derivative of this thing with respect to t? This is u sub tt xt, which is w sub t of x t t from our Leibniz rule theorem that we just invoked, plus the integral from 0 to t of w sub tt x t s ds. Okay. Now you might say, why in this application of the Leibniz rule was there no extra term here, right? In the theorem that we quoted, there was an extra term. Oh, but the extra term here, right, was what? This extra term was w x t t, but if we go back to what we're assuming w solves, oh, that's 0. Right? That's 0. So that's why we didn't have to add anything to it here. Okay, and so we get this expression here. But actually, by that same fact, w sub t of xss is f of xs. So w sub t of x of tt is f of xt. So this is f of xt plus the integral from 0 to t w sub tt x t s ds. And now it becomes clear what it is that's going on here. Right. So let's go back to this expression here. Okay. So what is u sub tt minus c squared u sub xx? What is that? Well, u sub tt is this thing. So that is f of xt plus the integral from 0 to t of w sub tt x t s ds minus c squared times u sub xx, which is this thing. Right, the integral from 0 to t of w sub xx xt s ds. So then putting this together, this is f of xt plus, this is the integral from 0 to t of w sub tt x ts minus c squared w sub xx xt s ds. Oh, but by this equation we're assuming w solves, this is 0. Right, this is exactly this wave equation that it solves, so this is equal to 0, and so u sub tt minus c squared u sub xx is f of xt. Okay. Now, note, what is u of x0 by this definition? Here's what u is. U of x0 is the integral from 0 to 0 of stuff. Who cares? That's 0. And u sub t of x0 is, u sub t is this expression, which again is integral from 0 to 0 of stuff. Who cares? That's also 0. So u satisfies the initial, or sorry, u satisfies the PDE, and it satisfies both initial conditions of 0. And so it does indeed solve this expression here. Okay. So we've proven Duhamel's principle, but we haven't seen exactly how Duhamel's principle leads to that extension of D'Alembert's formula. That's something left to you as an exercise in one form or another. So you can have a look at that. I believe this is exercise 17 in the chapter 3 material. So there is another way to do derivation of Duhamel's principle that involves Green's theorem. You can have a look at that if you want. That's on pages 99 through 101. So pages 99 through 101 is another proof of Duhamel's principle using Green's theorem. You can have a look at that if you want to. Okay. Now, one more statement I wanted to make about the niceness of the wave equation. So let's return to a question of well-posedness and what's called time reversibility. Of the wave equation. Okay. So recall that what does well-posedness mean? So first, existence of solution. We already know that. 2, uniqueness. We've actually proven this in a variety of ways. You could say that D'Alembert's formula, right, tells you that this thing is unique, right off the bat. But also we've shown this energy method, right, is another way for getting uniqueness of solutions. And then lastly, continuity with respect to small perturbations of data, right? So stability with respect to small perturbations of the data. So we can do this directly with D'Alembert's formula. So existence and uniqueness is already, that's taken care of by us. So the question then is stability. We can use D'Alembert's formula. Now, I'm not going to go too heavily into this right now. You can read up on this expression, the statement of stability, if you like. This is on page 101. If you want to see this discussion of stability. But basically, we take perturbations of our phi and c and show that that leads to correspondingly small perturbations in the solution. Okay, as you might imagine, this is an epsilon delta style statement about, it's almost like a continuity statement with respect to that equation. So as I said, I'm not going to, if you want to see that stability statement, you can have a look at it on page 101. But we get all three of these things, and so we're happy here. Now, the other thing that is something to think about is time reversibility. This is not going to be something in general that's true for like every PDE. We're going to see at least one PDE for which this is definitely not true. And so what is time reversibility? Time reversibility is a question corresponding to a problem something like this, right? So let's consider a backwards problem, right? A backwards wave equation. You might think this in the sense of it's like a bizarro wave equation, but it's not really in that sense, right? It's still the wave equation. Okay. So x in RT is less than or equal to some t naught, and u of x t naught is phi of x, and u sub t x of t naught is c of x. Right, here's a backwards problem in the sense that I'm given displacement and velocity at time t naught, and then I'm asked to solve this equation for t before t naught, right? Well, it turns out that this equation is also well posed. That is, I have existence, uniqueness, and stability of solutions to this thing. Okay. So, this is what it means to say that our wave equation is, so wave equation, or specifically the IVP associated with it, wave equation is completely time reversible. Now, you might not view this as particularly surprising. One, from the context of what it's describing, right? You might say, oh, yeah, right. If I believe that this, is modeling what I think it is, right? What my intuition tells me it is, then this isn't that surprising. But also, you can notice that another way to see that this is completely time reversible is, what if you make a change of variables here, right? So change of variables. So what if you make a change of variables, s is the variable minus t. If you do this change of variables and see what comes out of the wave equation, what do you get? This leads to the equation u sub ss is c squared u sub xx. Oh, it's actually the same equation, right? And so you can either, like I said, you can either say from physics, I know that this should be time reversible in this way, but also just from the equation itself, knowing absolutely nothing about physics, if I just do a change of variable where instead of going forward in time, I'm going backward in time, the equation that should be satisfied is exactly the wave equation, so it doesn't matter, right? Going forwards and backwards in time, there's no problem there swapping between the two. Okay, and so what is the next thing? What's the next thing I'm heading towards, right? So I'm not going to be able to do uh, much there today, but this is where we'll start next time, and we will finish chapter 3 next time. This is our first example of what happens if instead of an infinite ideal string, I have at least one fixed end. Right? So, for instance, consider the IVP slash BVP. Remember, BVP is boundary value problem. That looks like the following. Let's say that we have V sub tt is equal to c squared v sub xx with our typical, and this is going to be for, instead of for x in all the reals now, this is going to be for x non-negative, for t positive. Okay, so v of x0 is, this is my initial displacement, this is my usual displacement function phi of x. The initial velocity is c of x. And now I have a condition at that fixed end. So here, right, is my fixed end. I have some condition there. Let's say that my condition on the displacement at that end is that the displacement is 0 there. Okay. So what is the difference here, first of all? Well, everything we did previously assumed that x was in the entire real. So when I drew the xt plane here, of course I've drawn this just to show, but when I draw the xt plane here, what is it that is happening is now, instead of having all of these values x over here to worry about, I don't have any of those. I don't have any of the negative values of x. I just have this. And so those formulas that I had written out technically are to solve the ideal case, right, of the infinite string. And so I can't just blindly apply, say, D'Alembert's formula, right, because D'Alembert's formula doesn't really apply to this problem, right? D'Alembert's formula was specifically for the case of having an infinite string. So this is a little different, right? I have to think more carefully about what it is that's going on here. So this is what we'll do starting in tomorrow's lecture. We'll do one fixed end, and then we'll see what's going on there, and then we'll do a finite string, 2 ends, and the different types of boundary conditions that can arise there. And then we will be done with chapter 3, and we'll move on to higher dimensional wave equation, which we won't spend too much time on until we revisit it much later. So anyway, that is the deal for now. So I'll post your next homework soon, the next couple hours. I'll send out an announcement when I do that. So until then, I'll see you all tomorrow.